Okay, so how did the homework go?
It was cool.
Cheddar cheese.
Pseudo recursion makes everything easier.
Yeah, so the solution should have been fairly short, right?
Yeah. Short as
It
well.
works, but I don't know how it works. But it works.
All right, so let's talk about it. The overarching statement I might give here, and this is more of a mindset thing. So let's call this a tip. If you have a function that performs a task and you need to complete that task, call the function. I'm going to swing back to this here in a little bit after we dive into the code and see the result here. Let me. All right, so here's our binary tree stuff. We were supposed to implement what the display in order, display pre-order, display post-order. Do I already have that in my CPP? Yeah. Okay. So what we want to do is for display in order. Well, we'll just do that one first. So display in order, if we go back here and think about this, display in order says visit yourself, then your left child, then your right child. And what we mean by visit is print, display, whatever. Okay, that's what this guy is doing, is displaying. So in order says display me, then ask my left child to display himself, then ask my right child to display himself. So from display in order, how do we display me? It's C out. All right, so to display ourselves, we're going to display our payload. And let's put a space after that, maybe. Then we want our left child, who is a binary tree, to display himself in order. How do we do that? We say this left child display in order. Then I want to have my right child, this right child display in order. If you have a function that performs a task and you need to complete that task, call that function. What does display in order mean? Display in order means display myself, then my left child, then my right child. What kind of animal is my left child? It's a binary tree. Can binary trees display themselves in order? Absolutely. Who does it? This guy right here. All right. And then we come out here to driver CPP. And we say the tree display in order. Just make sure it's in that guy. Oh, of course we're going to get that. Because you only can do this if you actually have a left child and a right child. So if this left child, then display in order. If this right child display in order. So there's our values being displayed in order. Actually, let's say in order is left, then me, then right. Left, then me, then right. That's in order. So there's the guys in order, right? We happen to get the numbers sorted. All right. So the other one's going to be the exact same. Oh. Pre-order is what we originally wrote. So that means visit ourselves first. Then visit left and right. And post order means visit left and right, then ourselves. And just kick it down the line here. Retrieve, display pre-order. Display post order. And I'll give it one more kick down the line. So there's our 3 different traversals. Okay, so again, if you have a function that performs a task, and you need to complete that task, call that function. What does in order mean? In order says, visit my left child. Do I have a function for displaying my left child? In order, I do. Actually, hold on, we actually have a bug right now because I copied and pasted. This guy should all be pre-order. And this guy should all be post-order. There we go. So we had a little bit of a other visiting orders there. Okay, so visiting means if we're visiting in order, it means we're going to ask a tree to display himself in order. We already have a function that does that. What does that do? It asks his left child, if he has one, to display itself in order. Then it displays himself. Then if he has a right child, it has him display it in order. We already have methods that display binary tree in order. What do you do if you want to do that? You call the method. All right, so this is that pseudo recursion we talked about last time, where I'm calling the same function, but it actually belongs to a different tree. It's not this particular guy's display in order function. It's another tree. It's my left child's display in order, or it's my right child's display in order. But display in order itself, the logic of display in order is easy. It's deal with my left child, deal with myself, deal with my right child. All right, so I think somebody said they don't know why it works at the beginning. Does it make more sense now, or are we still confused? I'm gonna take that as,
I think it was kind of confusing to me because of how short it was, but the recursion is helpful in understanding it. I think
yeah, I mean, that's kind of the punchline of recursion, is that, I mean, when we first talked about recursion, or last week or whatever, a couple weeks ago, whatever it was, I mentioned that typically recursive solutions tend to be relatively short and elegant. You know, they almost look impossibly short because all the logic is built into the recursive calls. But they are memory inefficient in that every single, like when I had to call my left child display in order, this entire copy of this function got put on hold because we had to wait for this guy to finish. We didn't get to this line until we dealt with the entire left subtree. Does that make sense?
yeah.
Very first thing I did each time was my left child dealt with his left child, who dealt with his left child, who dealt with his left child, until he finally got to a situation where he didn't have a left child. Then he was able to deal with himself. Then he dealt with his right child until he didn't have a right child. Only then were we able to go back up a level for the other person to deal with himself and his right child. Only then were we able to go back up a level for him to deal with himself and then his right child, so on and so forth. So there's potentially a whole lot of waiting here and a whole lot of waiting here before this function can finish, because this is going on another adventure to tell this tree to display himself in order.
Could this cause a lot of problems if you had like a very large tree
Well,
with like time?
what do you mean by problems?
Like time. Could it be very inefficient time-wise as the tree gets larger and larger?
Not time-wise. Memory-wise, definitely. I mean, time is not a big problem. I mean, whether we're asking this object to display himself in order or we're doing some iterative thing, time is going to be the same. I mean, we're speeding through it logic's logic, right? But memory footprint, if every single time we make a call to this function, we have to put this entire guy on hold, that's going to equal memory inefficiency. You know, because effectively this guy is overeating. Every single time we make a call to one of his children's functions, you know, this guy uses more memory. Does that make sense?
Mm-hmm.
So I guess my follow-up question for you would be, is that bad?
So like, couldn't you get an overflow error if the tree was very large though? Because it might just,
If you didn't have a big enough stack, yeah, your operating system uses a stack data structure to put things on hold that have to leave the CPU to be processed later. So in the operating systems class, you talk about certain things that, you know, have to wait to be completed, like user input. So I/O is something that takes time. So if you have a computer program that says, you know, please press enter to continue, that computer program would be wasting its time sitting on the CPU any longer because it needs to wait for the human being to press enter. And we don't know if that's going to happen in a second or in an hour or ever. So it's not going to sit there and tie up the CPU while it's waiting on something. So it's going to context switch off the CPU and kind of have to put everything on hold for that particular program that's running on the CPU. Well, the same thing's kind of true here. When we can't take another step forward, I can't get to this closing curly brace until this guy has completed. So I have to be able to pick up where I left off, which means I need to put this entire thing on hold. And the way that's done is through the computer's stack data structure, that it keeps in system memory. So it takes up a portion of your system memory as a stack to push things that are currently on hold onto there so I can come back and get it later. Well, if your stack isn't big enough and you try to push too many things onto that stack, you're going to run out of memory, or you're going to start getting segmentation faults because you're going to walk off the end of your stack and start bleeding into, that's kind of like a memory leak. You start bleeding into other parts of your system memory that you didn't know. So the answer is yes. I would say any kind of problem where you might be making recursive calls, let's say making many recursive calls. The question is how much is many, right? You know, what's too many recursive calls? It's probably going to depend on the nature of the problem of whether you're forcing recursion or recursion is just the way to do it. But, you know, generally speaking, very, very, very large problems. If you looked at a problem, you said, this is really, really big, you probably want to avoid recursion. If you can say true in your head that this is a really big problem, recursion is likely not a good solution because of its memory footprint. Now, the good news for us today is that our computers have a lot of memory. And for example, I think you could do this with a flag on the G++ compiler as well, but like the Java compiler, you can give it a runtime flag to increase the stack. Let's see, I might be able to show that to you. JavaX on here, right? Is it Java -H? Yep. Rep for stack. Does it really not pipe it into one of these options lets you specify the stack size. All right, -X gives you all the options. Here's one example of heap. You can set the heap size. That's where your objects and stuff are actually stored. This might affect the stack. Yeah, here it is, stack size. Dash X S size sets the stack size. Actually, this is specifically for threads. There's probably another one, but no, this is the, or maybe it implements recursion through threads. So this allows you to specify a larger stack size. You can give it that's a 1 megabyte stack size, which would, if you say the size of a function call is, I don't know, we'll just make something up. Let's call it 100 bytes. That means if it's 100 bytes, you can have 1,024 kilobytes times 1,024 divided by 100. So then you can make, over 10,000 recursive calls before it becomes a problem with a 1 megabyte stack. So if you just need a bigger stack, just give it a gigabyte stack, right? So we have enough system memory in our computers to handle many, many, many recursive calls. Memory isn't really that big of a problem now, but Java is a good example in that Java runs on a virtual machine. So since it runs on a virtual machine, we can tell Java, what size of a stack we want you to use. Where C++ don't run in a virtual machine. They run directly on the operating system. So we don't necessarily get to choose what stack size to use. It's possible G++ can give system call, let's see. I'm going to pipe the output of that. That did it, right? Yeah. No, it's not in there. There's nothing about stack in there. So, let's see just real quick what kind of things we can look at. Program name. And actually the stack size, and that when we were looking at Java, we weren't looking at the compiler, we were looking at the runtime. The Java is the actual executable for running something in the Java virtual machine. Yeah, so we would be stuck with the operating system's stack size, and the operating system stack size is what the operating system stack size is. You could probably go and edit some configuration file on Linux and change the default stack size for it, and then reboot the OS, and it'll claim more of your memory for a larger stack. You can do that kind of stuff.
So, to use the Java example, if you're doing like Android development, do you have to be more careful with recursive calls because there's obviously less memory on most phones?
Well, sure. I mean, that's a true thing, but I mean, again, I think it probably still falls into the the world of, if the problem you're solving is really big, if you can say true, this problem is really big, you probably want to avoid recursion. But for problems that are where recursion is convenient, chances are they're not too big.
Okay.
So I don't necessarily think it's a wildly common problem. I think it's more of a you need to be careful because of how recursion works, but you don't need to be that. You don't have to walk on eggshells around recursion. Okay, so any other questions about tree traversal for binary trees? Okay, and we saw the in order gives us the tree sorted. So effectively, that's a sorting algorithm. If we go look back here, display in order, this is a sorting algorithm right there. And if you think about previous sorting algorithms we've looked at, like our modified insertion sort, where you have the follower and bubble things up towards the top and all that jazz. That's a significantly more complicated algorithm. Where this one is super easy because we follow the rules of how something gets added to the binary tree. It follows the binary tree rules. Visiting it in order gives us our data in sorted order. Okay, so this data has structure to it. All right, so now we're going to look at and I think I mentioned last time, there's lots and lots and lots of different twists on trees. So binary trees follow this rule that allows us to, there's built-in structure into the tree. But, there's lots of different kinds of trees that we can use for different types of stuff. So for instance, other tree uses, we might say anything that requires a organization chart. So we might say something like a business has an organization chart where like maybe the president's at the top and then there's some VPs, so there'd be nodes under the president, and then under VPs there'd be some assistant VPs or something like that, all the way down until you have the people that are stocking the shelves or something like that. So there's a hierarchy to a business, and you can use that to show trees. File systems. So for instance, if I go out here to Linux and I go to the root directory, which is this guy, inside here, so I have the slash directory. So if we drew a picture of this, so the slash directory in Linux is kind of like the C directory in Windows. Okay, so from the slash directory, I have, let's just pick a couple of them. I have bin, Etsy somewhere here. Bin, Etsy, and let's pick one more. Dev for devices. So I'd have the bin, Etsy, dev. And then if I go into the bin directory, you see we got a bunch of things in here, and these are leaves. So anything green is an executable. So these are actually files that live in there. Okay, so instead of it being a directory, these are files. I go up and I go into dev. Here is a another thing. So I go into CD-ROM. So inside here, we have an input directory, so on and so forth. So we can map out our directory structure in a tree. And this would be an n-ary tree because we don't necessarily know how many things are going to be at this level and how many things are going to be at the next level and so on and so forth. All right, so things that have representation we can do as a tree as well. Binary trees follow a rule. Trees give us a way of storing things in a structured way. So now I want to talk about I want to remind us, what's a data structure? So far we've talked about linear linked data structures, linked lists, stacked queues. We've talked about non-linear linked data structures, trees, so n-ary trees, binary trees. We talked about self-balancing trees. We didn't write any. We might come back and do some of that, but I want to make sure we get through all the different things. What's the purpose of what we're writing? Why are we writing stacks and linked lists? And what's the benefit of a linked list? Why did we write that? Why do we need a linked list? Somebody.
Store stuff.
Okay, store stuff. Didn't we already have a way of storing stuff before?
Variables.
Okay. Well, so what's the limitation of variables that made us look at maybe linked lists? What could a variable do? And what did we want it to do that linked list can do? Or what can a linked list do that a variable can't?
Can store
It
stuff in a
can-
more useful way.
Okay. What does that mean?
Like, because linked list gives us a tool to be able to process the data in more of a efficient and useful way.
What makes it efficient?
Because rather than just having a bunch of different variables out there in memory and having to call all of them separately, now we can put them all into a box and say, this is our box.
Okay, so a linked list lets us store multiple pieces of information. A variable can store one piece of information. A linked list can store multiple pieces of information.
Yeah.
Okay. Well, didn't we have a way of storing multiple pieces of information before linked lists?
Linked list lets us do it in non-contiguous memory.
Okay, so we had arrays, right? So we had variables which let us store one thing. Then we have arrays that let us store many things but require contiguous memory. So linked lists don't require contiguous memory. Why is that a benefit? What's the perk of having non-contiguous memory?
We don't have to know how much we're going to store in it when we originate it.
Yep. So we look at arrays, we say, hey, these things are great. They let us hold a bunch of stuff, but in order to be somewhat efficient with it, I need to, and maybe it doesn't even matter. You know, we have plenty of memory today. We just talked about that. So we can just throw a whole bunch of crap in there. And if we have to keep destroying it, no big deal. That's the computer's problem, not ours. But, you know, we can say, you know, because our arrays give us the convenience limitation of having to know how many things you're going to store before you start filling it, or overbuilding, right? Just like in real life, if some people might go and buy a house, you know, a recently married couple maybe go and buy a bigger house than they need because they're planning for 2 or 3 years in the future where they might start a family. So they figure they'll grow into the house, right? Something like that. You know, so you could just create a larger array than you need and then grow into it. But you know, if you always want to have something that kind of holds the correct amount of stuff that you have, maybe a linked list fits that need, with the caveat that they're going to be slower, because linked lists, we have to traverse through memory to get to places. We can't just calculate where it is. We're giving up that contiguous memory thing. Gives us speed, but it also gives us a limitation of having to pre-request our land. Whereas a linked list takes away that speed advantage, but says, hey, you can just elastically grow as you need to grow. Okay, so that's talking about a specific kind of evolution of a data structure, going from being able to store one thing to being able to store many things contiguously to being able to store many things non-contiguously and having the benefit of that. So if you were to kind of generically tell me what the purpose of data structures are, what would you say?
Hold many numbers in an organized way so that we can manipulate them easily.
Okay, but is it only about holding numbers? So let's say you have, you know, you just finished dinner and you have some leftovers. What do you do with them? We got options, right? You can say, I don't eat leftovers, I'm going to pitch them. But let's say you're going to store the leftovers. You're going to eat them later. What are some options you can do with the leftovers?
I'm gonna put them in like a container of some sort.
Okay.
Or,
Get like a Tupperware container, something like that. One of these things that has, you know, it's plastic, has the lid on it. Throw it in there, and those things come in different sizes too, right?
right?
You kind of pick the one that's roughly the size you need, right?
Yeah,
And
pretty much.
and you store it. Okay. Any other options? So you can pick a container, preferably a container that's the right size. But hey, in a pinch, you can use, you know, you have this little tiny leftover. You can use the biggest Tupperware container you have. No big deal, as long as it'll fit in the fridge. Alternately, you can maybe wrap it in saran wrap or something like that, or wrap it in foil, or shove the whole pizza box into the fridge, or just leave the pizza box out and say, oh, I like cold pizza, whatever, and see what happens. But we have options, right? And each one of those has its pros and cons, and they might all solve the problem. But these are things that we use for holding things in real life, right? Our clothes, we have pockets, right? Pockets are for quickly putting something into, something that's got to be fixed in terms of size, but allows us to conveniently carry stuff around with us. So throughout our lives, we have these various structures that we use for holding things that, you know, they may not do anything all that fancy, but they do represent things. You know, we have a keychain, right? Keychain holds on to a bunch of keys because keys are easily lost. They fall around and stuff like that, but they don't necessarily by default hold keys in any sort of specific order, right? You know, there's some organized keychains, but in general, you kind of have to flip through to find your keys. Or you've seen people that get the little color code things for their keys. So they, you know, the yellow key I used to get in the house, and the red key I used for the office, or, you know, something like that. So these are all real life versions of data structures. These are tools that let us solve problems, right? They're no more than that. Okay? These are organizational structures that try to make our life easier. And the fact that we have given some of them names is relatively meaningless. The fact that we have a name called stack and that has connotation, name linked list, name is a queue. These are things that just have been around for a long time. We had to give a name to it, and you know, whatever. But every single time we create an object, you know, we create one of our objects, that's a data structure, is it not? You know, go back to when we, you know, were first learning about objects, we created, I think one of the first objects we created is like a fraction object, right? We decided, hey, I need a container that's specifically built for holding fractions. It needs to hold the numerator, it needs to hold the denominator, okay? You have leftovers, and you have a solid food, and you have a gravy. Well, you might not put those together, or maybe you do, but maybe you want to have them separate, right? So you might have a container that has two halves to it or something like that. That allows you to conveniently store that in one container with some separation within the container. it's very customized. Maybe it's something that has some limits to it in that, you know, you might have a fairly big container, but if only half of it is usable at once, you might not be able to fit as big of stuff in there, or you have to split it between the two halves or whatever. You know, you have to work with the tool that's in front of you. But these things all solve some problem for you storing things and carrying them around with you, right? So you're not carrying handfuls of spaghetti, you have it in a container, all right? So that's what data structures are. This is a generic way for us to store data. We have the traditional data structures. Then we have the ones we invent for holding all sorts of things. That makes sense? So don't get caught up on this idea of you know, data structures being part of this like very exclusive club. Almost everything that we write is a structure for holding data in computer programming. Because what are we doing? We are taking data and we are doing operations on it. That's what programming is. Okay? So, having said that, we want to think about a map. I'm going to do it on a different kind of slide here. So let's think about the map that is, I don't know, kind of this local area around the school. So the school is actually, well, we'll do it this way. The school is in Mequon. And kind of just north of the school is Grafton. North of Grafton is Port. I'm going to shorten it so I don't have to type it so long. South of Mequon, actually let's go west of Mequon. This is Germantown. Of course it was going to be too big. All right, so that's Germantown, kind of northish here is the Falls. Kind of down here-ish, we have Tosa. Over here, we have Brookfield. And we have Milwaukee, something like that. I know there's some, we've left out some players. So if any of you live in like West Dallas or something like that, just deal. You know, we also have then the east side over here, right? But we'll call this good enough. So this is a relative rendition of the area map, right? Okay. Now, so these are individual towns. What connects towns to each other?
Roads.
Roads. Okay. So we'll draw in some roads here. So do we have a road that goes from Port Washington to Grafton? A couple different roads, but let's just keep it simple and pretend like there's one road that goes there. Do we have a road that goes from Grafton to Mequon? Yep. We have a road that goes from Mequon to Milwaukee. We have a road that goes from Milwaukee to Tosa. We have a road that goes from Tosa to Germantown. We have a road that goes from Germantown to the Falls. We have a road that goes from the Falls to Grafton. We have a road that goes from Germantown to Mequon. We have a road that goes from Brookfield to Tosa. Let's say that's a rough rendition, right? You know, I know we have some other roads that kind of let us cheat a little bit here, but we're going to say this is the simplified map. We'll call these the somewhat direct roads, the smart roads to take, or something like that. Okay, so we would look at this and call this a map, right? If you jotted this down on a napkin at a restaurant, as if you're ever going to go to one of those again, then, man, that kind of makes me cry on the inside. Those of you who know me outside of school, I frequent restaurants often, so this is killing me. So, but you could jot this down on a napkin at a restaurant and show it to somebody. They would have a decent idea of how the Milwaukee area is laid out, right? We've omitted a couple of things like the east side and that kind of stuff, but generally speaking, this gives us a diagram-ish of the Milwaukee area. Okay, so now we would call this guy, in real life, we call this a map, right? In data structure world, we're going to call this guy, and actually there is a data structure called the map, but we're going to say this. We're looking at graphs. A graph is like a map in real life. Okay? Now, in real life, these guys are called roads. Now, are all roads two-way roads, or some roads one-way only? Some roads are one-way only, right? Now, the roads I've drawn here is, do we have a way of going from Port to Grafton and a way of going from Grafton to Port? Yeah, these are, so we have two different kinds of graphs. So we're going to say a graph is a collection of edges, and we can think of edges like roads. And just like in real life, graphs, and typically we actually deal with this at the graph level, whether a graph can be directed or undirected. So is a graph made up of roads that go both directions, or is a graph made up of roads that only go one direction? So a directed graph only goes one direction. Directed means you can only travel one way along an edge. Undirected, I'll kick it down in a second. Undirected means you can travel either way along an edge. All right, so that's the high level, let's say, description of a graph. Okay, now we already have given definition of when we might use a graph, right? We might use a graph to create a map. There's actually a famous problem that we'll talk about after we explore graphs a little bit in a more interesting way. But there's a famous problem called the traveling salesman problem. I'm going to spell traveling. Is it what? 5 L's? Oh, well. Sometimes you'll see it short as the TCTSP, traveling salesman problem. So this guy basically states that there is a salesman that has to visit each town on a map to do their sales. And they want to visit the towns in the most efficient manner given their starting location.
Can we keep it as salmon? It makes it a lot more interesting.
Now, what's missing from this map I have up here?
The other connecting roads to other towns, like say Port and
Yeah,
Falls.
let's say that I have all the roads here, but you're not wrong. The real map would be more complex than this. But so all the roads, what's really, say this again?
The starting spot?
For the traveling salesman problem, certainly the starting spot. So let's say I'm starting in Mequon and I want to go, I have to visit all these other towns to do my sales. Okay? And ultimately return home at night. So I need to come up with a game plan for where do I, when I leave my house, where do I go in order to ultimately visit every single town and get back to my home in the most efficient way possible. What does the most efficient way possible mean for the salesman?
The least number of miles, so you're not backtracking.
True. What's missing from this map?
Distance.
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 I've kind of drawn, kind of relative lines and stuff like that. But I mean, if you really, I mean, Grafton and Mequon are a lot closer to each other than Mequon and Milwaukee, right? So really, I need to have values here next to these. So maybe this guy is a, I don't know, let's say it's 7 miles. And this guy is what, 5 miles? This guy is maybe what, 17 miles. This guy is probably more like 20 miles. $11 miles maybe. We'll make those similar, but let's call that 15 miles. Call that 5 miles. Call that 8 miles, something like that. And this guy is probably 5 miles. Ish. All right, so these roads have a distance associated with them. These edges have a weight associated with them. All right, so graphs call these guys edges, and edges are like a road. They're going to have a value that might have meaning to it. Now, we're using a graph here to represent a map. And in that world, the value associated with an edge might be miles. Could we have more than one value associated with an edge? What other value here might be important? This kind of gets into the idea that data structures are an idea, but we might customize them for different things. Like we made our stacks for Towers of Hanoi play by a certain set of rules that deviated from the traditional stack.
Could it be like time for like traffic and stuff?
Okay, possibly. Is there a simplified way of kind of talking about that based on our roads?
Speed limit?
Speed limit. Okay, so going from Grafton to Port, I'm probably dealing with like a 45-mile-an-hour speed limit. Grafton to Mequon, it's the same. Mequon to Milwaukee, though, is, let's call it 70. It's the fastest, but you know, let's just say that's 70 miles per hour. Milwaukee to Tosa, most of that is 50. Tosa to Brookfield, I think it might still be 50, but you know, you get the point. You know, the number of miles in these roads is also it isn't enough information to know what's the fastest way from getting to point A or B. We might not, maybe the traveling salesman doesn't care about the fastest. Maybe he cares about the most efficient. He wants to spend the least amount of gas, something like that. Make sense? Okay. So what we're going to do is we're going to go back. Did you guys do a cave crawler in one of your classes? Oh, you know what I'm talking about. Okay. So maps are all fun and all. And when and if we talk about traveling salesmen in here, if not, you'll talk about it in like 490 or something like that. So it's you'll still get it. But we've already talked about it at the high level. But we want to be a little bit more fun here. So we're going to build a here, we'll get our Christian worldview in here. All right. Now, typically, we're going to have a starting point in our graph. All right. And actually what we're implementing here, if you want to go back and watch videos or something about these things, is something called a MUD, multi-user dungeon. So this is a game. This is like precursors to like World of Warcraft and things like that, where your guy was sitting there inside of this dungeon. You know, maybe the entrance is here and he would go north, he would go north, he would go north, then he could go south, west, east, or north again. And each of these rooms might have something in it. Maybe there were monsters to fight or something like that, right? All right. So this is our map. All right. So we've created this map of our dungeon. Now so if this is a room and this is a room and this is a room, so on and so forth, what connects these rooms to each other?
Hallways?
Say this again.
Hallways? Or pointers?
Hallways, doors, whatever. Yeah. So there's going to be connecting pieces, right? So if you're in if you take the university as an example, you know, if you're in one place in the university, you might not necessarily be able to directly get to another place in the university. You have to go by way of wherever the exits are, and those hallways. But really, the hallways are rooms in and of themselves, right? You know, if you walk outside of computer science, you have that big long corridor there. That's a room. There's a big long room that you're moving within until you take an exit. Either if you go left down by their cafeteria or go right, so you're walking towards IT. The library, whatever, however you want to think about it. You know, that's how that building is organized, as a collection of rooms. All right, that makes some sense. Now I've drawn our thing here where all the rooms are the same size, but we can certainly imagine them as being you know, being different. In fact, actually, let me think about that. So, yeah, it's not quite. I was going to say that computer science isn't that far off from across. So if we were designing this to be computer science, you know, this is like maybe 120 down here. This is the esports arena. Here's the hallway going down here. This is 118. This is the computer lab, and the computer lab's actually kind of a double room there like that. So this is like the front half of the Mac room. This is the back half of the Mac room. This is that little side room. Then we have the 3D printer room, well, the old 3D printer room back behind that. So this is 120. This is 118. This is Mac Lab, call that 2. This is Mac Lab 1. This is Advanced Lab 2. Lab 1. This is hallway. We'll call this guy hallway 2. Hallway 1. Hallway 0. This is esports. Then you do have a couple other rooms in here. So this is kind of a, maybe this is, I don't know what we call this, maybe lobby. Kind of a weird thing, but let's just go with it. This is server room. Then we have a little room here that used to be Dr. Locklear's office. In fact, we'll go ahead and put that there. I have a feeling this might be where our boss fight is. All right, so, and then we have, really from an organizational perspective, we're probably actually missing a little something here. So this is hallway 1.5. This is hallway 1.75. And you can name these things better if you'd like. This is the entrance to computer science. Coming into that, that hallway. So this is probably not a great representation. 120 is actually on this hallway out here, but just go with it. Just assume this is what computer science looks like. All right. Now, if we think about this as computer science, only some of these rooms are connected to each other, right? So this hallway attaches here. These guys are attached to each other. These guys are attached to each other. Technically, these guys are attached to each other.
So since they're doors, are they all undirected?
Yeah, we're going to implement this as undirected, but I mean, you could have a situation where, you know, you might have a I don't know, some kind of airlock or something like that, where, you know, you do have a place that is only one direction. So we're going to be creating a graph that is a representation of the computer science department. But yes, what you're asking is, if since it's a door, if I can go both directions in real life, it would be a undirected graph. So I can go this way. I can go this way. I can go this way. I can't go from this advanced lab to the Mac lab, but I can go from advanced lab 1 to advanced lab 2. I can't go from 118 to the server room. Actually, there is a door here, but nobody uses it. There's file cabinets behind it. So you can't go from the hallway to the server room, but you can go from the hallway to this lobby area here. You can go from the lobby area to this office. And you can go from the lobby area to that guy. And you can also go from there to the server room. Now, keep in mind that some of these rooms are sometimes locked, right? So for instance, you need to have a key to get from the lobby to the server room. So taking this exit, taking this door might require a key eventually as we evolve this. Okay, but right now we'll just assume everything is all put together. Oh, I'm missing a. You can go from hallway to 118. All right, so we're going to say that this is roughly our computer science department. Okay, so what we want to do is we want to create a graph that is a representation of the computer science department. So what is this guy? This guy is a collection. We're going to call them rooms, because that's probably what we call our object, right? We call it a room. This is a room. This is a room. This is a room. And a room has a collection of doors. And right now we're going to assume that all doors are two-way doors. They can go both directions. I can go from this, through this door, I can go from 120 to the hallway, or I can go from the hallway to 120. All right, so these are a collection of doors. Eventually, we're going to say some doors require a key, but we're not going to do that yet. But we want to be able to traverse through our department. So so it would be like a student, right? That would walk through this, these doors, right? So you have this entrance from the hallway. So this is that, initial hallway area. So who's going to be in here? We want to have a student can walk through the department. Okay, so that means that each room will also have a collection of inhabitants, right? So right now we're going to say all these rooms are empty, but when I first walk into the hallway here, now I'm in this room. When I leave this room through this door to get to this room, even though there's not really a door there, I'm just, I'm making my way down the hall, and we're representing the hall as multiple rooms. When I take this door, I've now left this room, and now I'm in this part of the hallway. If I go to the right or to the north, you can decide how you want to represent these. So if I go to the right here, I will be at this room. If I go west, I'm in this room. If I go east, I'm in this room. If I go north, I'm in this room. From this room, I can only go back south. I can't go to the west, even though I know there's physically a room to my west. I don't have a door that leads there. All right, that makes some sense? Okay, so for Tuesday, create a collection of objects, including at least room, door, and student, and allow the, let's see, and create a map. You can design the map however you want. Here, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. We'll say of at least 15 rooms. That a student can traverse. When a student enters a room, they should see the title of the room. So S118, so on and so forth. The obvious doors leading out of the room. And any other inhabitants that might be in the room. Right now, our department's not populated with anything other than us. So initially, when we first enter the map, it'll say we're standing in the hallway. There's an exit to the west. If you think about the map like deep down, like I'm looking at it here, there's an exit to the west. Then it'll ask you, what do you want to do? So you should be able to type in the direction and say west, and the student will move from this room to this room. Prompt the student for where they want to move. North, south, east, west. All right, so I should get dumped in right here. I should be able to say west, now you're in hallway 1.5. I should be able to say north, now I'm in hallway 2. I should be able to say west, now I'm in 118. I should be able to say east, I'm in hallway 2. I should be able to say north, I'm in Mac Lab 1. We're missing a little connection piece up here. All right, so we're creating a map of whatever dungeon you want to make. I've represented the computer science department. Yours has to have at least 15 rooms. And you're going to have an entrance point, and then you're going to allow your person to walk around this map. That's going to be our starting point. Make sense what I'm asking you to do? And you get to invent this however you want. Notice I'm not giving you a coding starting point. All right? So
We could use
go ahead.
So we could use linked lists or trees or any kind of data structure.
You could use linked lists and trees and other data structures in this, but I'd encourage you to remember this slide right here. What is a data structure? And recognize that this is a data structure. This is a node with one child. This is a node with 2 children. This is a node with 4 children. Okay, this is a graph, what we're creating here. All right, so we're pulling that idea that it doesn't have to have a fancy name in order for it to be a data structure. We're solving a real life problem here where we're creating to gamify it, we're creating a dungeon we might crawl through. in the back of your head, we should think about what Dr. Locklear's weapon should be when we actually create the fight to the death here. All right. Questions, comments, concerns, bribes. Also, if you, I think I mentioned it last class, but if I didn't, make sure you mark your calendar for the senior seminar presentations. It is the Tuesday and Wednesday evening before finals week, so not during finals week, the week before. I'd like to have everybody at the Zoom things for that, if at all possible. If you have another class, that's reasonable. If you have another legitimate excuse, that's reasonable. I'm not requiring it. There isn't an assignment associated with it, but you'll be in my good graces, and alternatively on my naughty list if you don't show up. So show up and support the seniors.
Will there be food provided?
There will be. There will be food provided.
That's good.
I did update I posted the actual titles of the different talks. So several of them should be pretty good. I'm sure a couple of them would be duds, but show up anyways so you see what a good presentation, what a good project looks like, and what a bad one looks like, so you don't do that when you're a senior.
Where can we find the links to these?
Say that again?
Where can we find the links to this? Is it on Slack?
It's all over the place on Slack. It's in the 300 channel. It's in the 200 channel. It's in general. It's in the happy hour channel.
All right, thank you.
Okay. So I'll use that as an opportunity to remind you to be checking Slack often, because we put stuff up there often. All right. I will see everybody on Tuesday. I can't hear you if you're talking, Noah.
I have a question for study groups. Is there a way for us to be added to the CUW like Zoom plan? Because the 40-minute meeting time limit can kind of get annoying sometimes.
It's a good question. When you go into Zoom, there's a thing that says SSO login. So when you first open Zoom, you can like log into Zoom.
Yeah.
And there's something called SSO login. So when I go onto Zoom, I log in with that.
Okay.
I log in with my Concordia email, username and password.
Okay.
Try that, message me, let me know if that works.
Okay. I'll try it next time we do it.
If not, I'll figure out something.
Okay. Okay.
Even if it's, I mean, because actually you guys, worst case, you should be able to join my group, my like happy hour, because I think you can show up to happy hour even if I'm not there, right? You can join the meeting.
You used to be able to. Now that there's all this new security stuff, I don't know if it'll still let us.
Okay,
But we
well,
can try.
try that and let me know, because I think the only limitation is that I can only be in one Zoom room at a time. So that means if I try to go to my classroom and you're in the happy hour doing that, then you'll get kicked out, because I'll be starting my classroom. The alternative is, if I'm in class at the time, you can always just join my classroom and then go into a private room.
Yeah. Okay.
One of the breakout rooms. So there's a solution that exists here, but let's start off with try to log in with SSO. And
Okay.
I think Concordia has a site license. I mean, I think it covers everybody, not just faculty, staff. So you should be able to log in with your student username and password, but let me know if that works or not, just so I'm aware.
Okay. Sounds good.
You the full kit caboodle, 300-person limit, all that jazz.
Sweet. All right. Sounds good.
Yep. Any other questions? All right. I will see everybody later.